Hello everyone and welcome to Natural Resources Canada's e-training module on integration of renewable energy systems. This course has been adapted from the U.S. Department of Energy's Federal Energy Management Program training material on integration of renewable energy systems. This training is being delivered through the Natural Resources Canada Greening Government Services to help federal departments and agencies plan and implement projects that reduce the energy use and greenhouse gas emissions of their buildings, laboratories, other facilities, and vehicle fleets. Over the years, Natural Resources Canada has been successfully developing comprehensive methodologies, practices, and tools to reduce energy consumption and greenhouse gas emissions for the private and public sectors, including the federal government. Since 1991, NRCan has provided enhanced technical support to Government of Canada organizations seeking ambitious greenhouse gas emission reduction actions from their building and fleet operations. This training will support federal organizations to meet their commitments and lead by example. The federal government has committed to reducing emissions from their operations by 40% below 2005 levels by 2030 and by 80% by 2050, as outlined in the 2016-2022 Federal Sustainable Development Strategy and in the Greening Government Strategy. It is important to note that federal buildings represent almost 90% of the government's greenhouse gas emissions. Additionally, the Greening Government Strategy stipulates that departments will use 100% clean electricity by 2025 by producing or purchasing megawatt hours of renewable electricity equivalent to that produced by the high carbon portion of the electricity grid. This initiative also supports the commitment by Canada's federal, provincial, and territorial First Ministers to scale up efforts to transition to highly efficient buildings and zero-emission vehicle fleets as specified in the Pan-Canadian Framework on Clean Growth and Climate Change. This course will cover the topics of energy systems integration in 6 segments. We will start with an introduction to renewable energy, including key sources of renewable energy. The second segment discusses integrating renewables to an energy system, followed by a segment focused on impacts of renewable energy on electrical distribution systems. The fourth segment is on challenges and solutions to renewable energy distribution, followed by a segment of strategies to integrate renewable energy to existing energy systems. The final segment compares renewable energy technologies. The course finishes with a short quiz to assess your knowledge of the material. The first module introduces renewable energy, including some context on why jurisdictions integrate renewable energy and some of the factors involved. This segment also introduces the main sources of renewable energy and how these sources contribute to Canada's energy supply mix. Besides reaching federal climate targets, there are several practical reasons to deploy renewable energy systems on federal sites. Primarily, among these reasons is that almost all renewables involve reduced environmental emissions of carbon dioxide, as well as other pollutants like oxides of nitrogen. Another reason is to reduce energy costs, which can be calculated using life cycle cost analysis. Renewable energy systems become more cost-effective as utility companies gain experience with installation and operation and maintenance, and technology becomes less expensive. Renewables also insure against volatile fuel prices apparent in energy escalation rates. Although fee structures vary between provinces, utility companies generally pass along various charges of the cost of fuel and infrastructure improvements to customers through the fuel adjustment charge, which changes every month and can be very unpredictable. Renewable energy implementation can also hedge against rate increases. Renewables can protect against fuel supply shortage or interruptions of fuel supply by providing a secondary redundant energy supply. Economically, installation and operation and maintenance related to renewable energy systems employ local trades. There are many factors that impact what renewable energy is integrated to a system and how. How do you know what technology is best for your application given your facility's location, site, and energy load? One critical determinant is the cost of energy. If your facility is in a location where utility rates are high, it is likely that renewable energy technologies are a good investment. The viability of renewable energy technology also depends on your local renewable energy resources. While solar energy is rather uniform, other resources such as biomass and wind can vary greatly by location and be very site-specific. Liability also depends on the unique characteristics of the technology under consideration. How much does it cost to install and operate and maintain? What is the efficiency, performance, and lifetime of that system? Provincial and utility policies for interconnection, net metering, and charge structure will also impact renewable energy system selection. Compliance requirements at your site, such as the Canadian Environment Protection Act and the Historic Sites and Monuments Act, may also impact your renewable energy technology options. An important economic consideration is incentives that might be available through programs offered by the federal and provincial governments and utility companies. Information on incentives can be found with local energy providers and provincial and federal government web pages. Economic parameters, such as the discount rate and escalation rate for the federal sector, can also impact project viability. Finally, the viability of renewable energy projects depends on your department's policies and mandates. Check your department's Sustainable Development Strategy Plan to learn more. There are some cases in which on-site renewables can enhance your facility's mission and help meet its goals. In all cases, it enhances our mission to save energy and pollution or be a good steward of taxpayer money. But in some cases, on-site renewable energy might more specifically enhance a department's mission, such as extending the ability to operate in a power outage. How are renewable energy sources used in Canada? As of 2017, hydropower accounted for 67.1% of Canada's total renewable energy use. Next, solid biomass, such as wood, accounted for 23.1%, while wind power accounts for 5.3% of renewable energy use. Other sources, such as municipal solid waste, landfill gas, solar thermal, and ocean, including tidal, wave current, and thermal, account for smaller percentages of national renewable energy generation. The next part of this segment introduces key sources of renewable energy in Canada: solar, wind, and geothermal, and their capacity to provide energy across the country. Let's begin with solar energy. Solar energy is provided by the sun as radiated heat and light. To harness this solar energy, solar panels are used to heat water or provide ventilation to buildings, and photovoltaic technologies convert sunlight into electricity. A map is provided on the slide to illustrate photovoltaic potential across Canada. Potential for solar energy depends in large part on exposure to the sun, which varies across Canada due to latitude, elevation, and climate. On average, municipalities in Saskatchewan, Manitoba, Alberta, Ontario, and Quebec are exposed to the most amount of sunlight. The potential for solar energy is lowest on the coasts due to higher cloud coverage compared to more central areas. It is expected that more solar generation projects will be installed as the cost of solar PV continues to decline, making it more competitive compared to other generation resources. Also, policies and incentives in some jurisdictions encourage the installation of solar projects. The kinetic energy from the wind can be harnessed and converted into mechanical energy or electricity. To generate electricity, wind is used to move the blades of turbines, which then generate electricity. A collection of wind turbines is called a wind farm. Many areas of Canada offer significant wind resources, particularly offshore and along coastlines, including along the Gulf of St. Lawrence. The southern prairies also offer wind resources. However, wind turbines need to be located near existing electrical grids. As most of Canada's coastlines are remote, there are currently no offshore wind farms in Canada. The provinces with the most wind capacity are Ontario, Quebec, and Alberta. In 2018, Ontario had the most wind energy capacity with 5,076 megawatts of power, followed by Quebec with 3,882 megawatts of power. The bar chart displays installed wind power capacity in Canada from 2004 to 2018. The installed capacity of wind power has grown from 444 megawatts in 2004 to 12,817 megawatts in 2018. The amount of annual new capacity peaked in 2014 with 1,891 megawatts. In 2018, 578 megawatts were added. The total capacity of the Canadian industry is 12,817 megawatts. The last renewable energy we will discuss in this section is geothermal. Geothermal energy is generated from heat provided from beneath the Earth's surface or heat absorbed from the atmosphere or oceans. Electricity can be produced from steam that is naturally occurring underground. Heating and cooling can be provided by using the temperature differential between air or groundwater, such as by using air source or ground source heat pumps. The map shows the distribution of geothermal energy potential across Canada by end use. On the slide, we present types of geothermal resources across Canada. The highest temperature geothermal resources are in British Columbia, Alberta, the Northwest Territories, and the Yukon. That concludes the first segment of this course. The second segment is on energy systems integration, which will discuss some of the key considerations for integrating renewables, particularly from intermittent sources, into an energy system. Energy system integration addresses how increasing amounts of intermittent renewable energy generation can be controlled to realize energy cost savings and improve system reliability. Years ago, grid integration issues were not critical because renewable energy projects were small and often located in off-grid applications. But tax credits and other incentives have made it profitable to install large renewable energy systems in grid-connected applications. Challenges surfaced as buildings and campuses strive to integrate intermittent resources while still relying on the grid to meet demand at times when renewable energy resources were not producing. Historically, existing Canadian electric power utility systems were based on one-way power flow. Real power always flowed from the central generation plant through substations and on to loads. Today, distributed renewable energy systems inject power into the grid from multiple locations within the system. The variability and intermittency of photovoltaic or wind power means that the design and operation of renewable energy systems often requires more detailed planning. Advanced planning is also needed to accommodate sharp increases of renewable power into the grid when it is generated, and likewise, provide for continued load when renewable energy output suddenly drops off. For these reasons, many utilities are investing in the grid so that power and information can flow in two directions and the grid becomes more flexible and reliable. It is important to note that applicable standards are being adapted for two-way power flows to facilitate the integration of renewable energy. In collaboration with Canadian Standards Association, NRCan has developed and published a consensus standard for the interconnection of static inverter-based distributed generation systems as a national standard of Canada, resulting in amendments to the Canadian Electrical Code. These standards are important to designers of high-penetration renewable energy systems. Now let's discuss net metering. A net metering program allows electricity consumers who produce their own power from renewable resources to generate credits that reflect the energy their renewable systems provide to the grid. Net metering allows consumers who generate electricity from renewable resources to access electricity at any time, instead of when electricity is being generated from the renewable source. Net metering is used to encourage private investment in renewable energy, especially wind and solar, which are intermittent sources. In Canada, net metering policies are under provincial jurisdiction. Electricity customers who wish to install renewable energy generation systems and connect them to their local utility grid must meet the requirements of their local distribution company. Let's explain how net metering works in practice. When a net metering program exists, a building that generates electricity from solar, for example, can provide any excess electricity beyond their load to the utility. When the building's load is below their own generation capacity, they purchase electricity from the utility. The electric bill is calculated on the net difference between the two on a monthly or yearly basis. A building with ample PV might offset enough energy to bring its electric bill, based on consumption, to nearly zero. Under net metering, the building still uses electricity from the local distribution system on a daily basis, even though it does not pay for all of this electric service. Some perceive that this type of net metering policy incentivizes distributed generation at the expense of other ratepayers. To further illustrate how net metering can incentivize solar power, the tables summarize the prevalence of provincial solar energy incentives and net metering programs across Canada. Most provinces and territories in Canada offer incentives for solar power, which can be in the form of tax credits or rebates for every kilowatt hour generated. As of October 2019, all provinces offer incentives for solar power except for Ontario, Nunavut, and Newfoundland and Labrador. All provinces and territories have net metering policies except for Nunavut, where a policy is pending. Local distribution companies, or LDCs, have final discretion regarding capacity limits on individual sites given safety and infrastructure considerations. There are also both technical and economic reasons why every utility customer cannot net meter, which we will discuss next by using a case study. As previously mentioned, a building that participates in net metering uses the electrical grid when they are not generating electricity from solar, such as on a cloudy day. However, they are paying a reduced amount to the utility based on the credits they receive for generating solar energy. This may result in reduced revenue for the utility. However, the utility must still maintain the grid infrastructure, such as distribution lines which serve all customers. As a result, there may be a cost increase for all ratepayers. To illustrate the impact net metering can have on an electrical system, let's look at Nova Scotia's Enhanced Net Metering Program as a case study. Nova Scotia has an enhanced net metering program. The program allows customers of Nova Scotia Power to connect small renewable electricity projects to the distribution grid through a meter that can ensure the flow of electricity in two directions. Projects must be sized to meet no more than the annual electricity consumption up to a cap of 100 kilowatts. If a customer has multiple accounts with Nova Scotia Power, they can generate electricity to their other accounts as long as they are within the same distribution zone. A variety of renewable energy sources are eligible under the program, including solar, wind, tidal, wave, ocean-powered, run-of-the-river hydroelectric energy, and bioenergy. As of 2018, there were 581 solar installations participating in the net metering program. Together, these systems generate 5.3 gigawatts of electricity. Nova Scotia's net meter program is complemented by the Provincial Solar Homes program, which offers a rebate of $1 per watt of installed capacity. This case study illustrates the applications of a net metering program in a Canadian province. Next, we will consider the impacts on electrical distribution systems from integrating renewable energy. That concludes the second segment of the course on energy systems integration. The third segment of the course focuses on impacts on electrical distribution systems from integrating renewable energy. A renewable energy project impacts both the facility and the larger utility system. A utility might cite a range of impacts that limit interconnection opportunities. For instance, new sources of energy in the distribution system both increase voltage at the point power is injected and increase the amount of available current. Interconnection challenges become greater as a renewable system becomes larger and is located farther from a substation and a local voltage regulation device. These circumstances have direct implications for the utility. Problems include cycling of the equipment that regulates voltage and problems for voltage regulation and overcurrent protection schemes. Interconnection can also change the power factor required of the utility and increase the amount of required spinning reserve. This can have the effect of reducing the utility's overall revenue, which is based on consumption. Some utilities conduct integrated resource planning, which considers future customer demand and assesses options to meet that demand. All supply-side options, generation and transmission, and demand-side options, efficiency, demand response, and distributed energy resources, are considered equally. This process can play an important role in facilitating efficient growth of renewable energy resources in a system. Now let's walk through three examples of how a renewable energy project may impact a utility. As a first example of voltage regulation, consider that the utility must deliver power with high and low limits of voltage. Voltage drops along a power line as the load goes up, and the transformer must regulate voltage based on the load. Adding a PV generator to an energy distribution system can affect an existing voltage regulation scheme. PV generation on a circuit will reduce the load seen at the transformer and result in line drop compensation. This can push voltage to higher or lower than the imposed limits. As a second example, assume that a fuse limits the current coming from a transformer to a value that is less than what the line is rated for, 100 amps in this example. Interconnecting a generator somewhere down the line might add current in excess of what the line can carry and void the overcurrent protection scheme. In this example, even one additional amp would require the utility to change the overcurrent protection scheme. The third and final example is regarding the power factor. The utility generally provides customers with both real power and reactive power. The cosine of the angle between the two is the power factor. However, an interconnected generator only adds real power back to the distribution system, a fact that worsens the power factor. As a result, the utility must generate additional reactive power. However, this can be wasteful and problematic. Should the power factor be much different than 1, the utility will impose charges to offset potential problems. That concludes the third segment of the course on impact on electrical distribution systems. We now move to the fourth segment of the course on renewable energy distribution challenges and solutions. This segment of the course goes through the challenges and possible solutions related to distributing renewable energy that occur at 4 different levels. From small to large scale, these occur at the building level, substation level, grid level, and utility generation level. Download the latest research from CanMed Energy at the Varennes, Quebec Research Centre on the Integration of Renewable Energy Systems. www.enercan.gc.ca/energy/smart-grid/4565. Let's begin by focusing on the challenges and solutions at the building level. There are 4 areas of consideration related to the effects of high penetration of renewable energy on the electrical service to individual buildings. 1. Sizing of electrical system to the building. 2. Overcurrent protection on electrical service. 3. Voltage regulation. And 4. Wear and tear on reactive power compensation equipment. Starting with the sizing of electrical systems to the building, the challenge is that the electrical service to a building is designed to accommodate the peak load expected of the building, plus a safety factor for future load growth. For example, a building with a 1 megawatt load might have a 2 megawatt service. If the building seeks to offset 24 megawatt hours per day of energy with on-site solar energy, which occurs only over 6 hours per day, a 4 megawatt PV system, 24 megawatt hours per day divided by 6 hours per day, would be installed, and the electrical service, 2 megawatts, would not be sufficient to get the solar power out of the building. A solution would be to have the electric service to the building upgraded from 2 megawatts to at least 3 megawatts to accommodate the flow of solar power out of the building during the day. 4 megawatts minus 1 megawatt equals 3 megawatts. Next, let's cover the challenge and solution related to overcurrent protection at the building level. Coordination of overcurrent protection is an important consideration in the addition of renewable energy generation. During initial distribution system planning, a protection coordination study informed the location and settings of fuses, breakers, protective relays, and synchronized other protective equipment to isolate electrical faults in a planned sequence. The additional current from a renewable energy generator invalidates previous protection studies because it changes the amount of current available for conductors to carry and changes the location and settings of breakers to prevent excessive current flow. The good news is there are solutions to this challenge. New studies may be required in order to determine how the maximum current from a renewable energy generator increases currents flowing through the electrical system when a line becomes overloaded or when a fault, such as a short circuit, occurs. Results of this study should include any required changes to the protective system used to detect and interrupt current and isolate faults. The protective system may need to be reset or redesigned to properly set the coordination and timing of devices, such as protective relays, reclosures, circuit breakers, and fuses in a system to detect and isolate faults. Now we will discuss how voltage regulation can present challenges for a building integrating renewable energy systems and some solutions. Voltage regulation is often cited as the primary concern of utilities when considering interconnection of a renewable energy generator. PV systems can increase the voltage at the point where they inject power, and they can also fool control systems which are based on load on the substation rather than actual voltage at the site. Utilities are required to keep these voltages within a relatively narrow operating range. For example, a 120-volt service may vary from 114 to 126 volts, root mean squared. To mitigate these challenges, planning and modifications are needed to calculate and predict deviations in voltage at various locations on the distribution system as PV inverters inject power at their locations. Also, at the substation, the utility will study the need to install new types of voltage regulation equipment that is based on measured voltage rather than load. The intermittent operation of the renewable energy generator may cause increased cycling on the new or existing voltage regulation equipment. Various software tools that model power flow can determine cycle counts on voltage regulation equipment during changes in variable generation power output. If found to be excessive, one strategy to reduce cycling is increasing the delay time of the voltage regulators. For the last section on building level challenges and solutions, we will discuss wear and tear on equipment. Equipment used to actively provide reactive compensation for power factor correction can also cycle excessively due to high penetration of intermittent renewable energy generators. The reason for this is that most installed PV systems with static inverters supply power at unity power factor, or PF equal to 1. This means that these PV systems can supply real power to loads, but not reactive power, which must still be supplied by the substation. To manage this challenge, the reactive power supplied by the utility must increase to accommodate each additional kilowatt of PV as it varies widely and suddenly as the renewable energy resource changes. Another solution is to specify inverters that provide reactive power if needed. This concludes our discussions of challenges and solutions for integrating renewable systems at the building level. Next, we will look at how substations manage integrating renewable energy. There are two areas of consideration related to the effects of energy system integration for substations: local effects and network protectors. We begin by discussing the effects of renewable energy on the local substation. The challenge is that an electrical substation consists of a transformer by which voltage is converted from transmission to distribution voltage, as well as a bus with circuit breakers, current transducers, and isolating switches on each circuit coming off the bus. Configurations, including transfer buses, double buses, and ring buses, are available, but because they are simple and inexpensive, single bus configuration is common. This single bus may serve to accept power from circuits with excess renewable energy and deliver it back out to the circuits with excess load. A substation is not designed to conduct this transfer if it was designed for power to flow only out to the circuits. The solution to this challenge is to reconfigure bus and circuits. In configurations other than a single bus, sectionalizing switches or isolation switches must be positioned for this exchange of power to occur, and new legs between circuits may need to be added. Analysis of expected renewable energy generation and loads may inform required reconfigurations to the buses and circuits. The intent of this reconfiguration would be to allow power to flow from circuits with excess renewable energy generations to other circuits with load to serve. Now let's discuss the other challenge at the substation level: network protectors. Substations and network systems, rather than purely radial, have network protectors on each circuit leaving the substation to prevent a reverse flow of power. Integrating renewable energy into a network power system may require special controls to prevent the renewable energy power from ever exceeding the load and potentially tripping the network protectors. This can be achieved most simply by installing an inverter with a capacity less than the minimum coincident load, but may also be achieved with advanced inverter features that allow the inverter to be turned off or modulate its output not to exceed the load. Now we move from discussing challenges and solutions at the substation level to the grid level. There are two areas of consideration related to the effects of energy system integration for grids. 1. Voltage stability of the electric grid, and 2. Synchronization of generation equipment on the electric grid. We begin by discussing voltage stability of the electric grid. Voltage stability refers to the ability of the grid to resume nominal voltage levels after disturbances, such as sudden increase in load or sudden decrease in generator output, or other demands for reactive power that cannot be met. Renewable energy generators that are inverter-based have voltage set points, which could trip offline during abnormal voltage conditions and exacerbate a low voltage problem. A possible solution is for new inverter standards to allow inverters to contribute to recovery from such a disturbance by riding through low voltage or low frequency conditions. Such inverter standards involve non-unity power factor, low voltage ride-through, and low frequency ride-through. Note that NRCan developed and published a consensus standard for the interconnection of static inverter-based distributed generation systems as the national standard of Canada, resulting in amendments to the Canadian Electrical Code as it relates to inverter-based distributed energy resource systems. Next, let's discuss synchronization of generation equipment. Rotor angle stability refers to the ability of the generators in a power system to maintain synchronism after disturbances, such as a drop-in frequency caused by addition of a large load or drop in renewable energy output due to natural fluctuation in the renewable energy resource. Output of inverter-based renewable energy generators can change very quickly, in turn affecting generator dynamics. With high penetration levels of inverter-based renewable energy, effects on synchronization of all the equipment on an electric grid may be significant. In terms of solutions, utilities can use commercial software packages in order to simulate transient events, such as a sudden loss of output from a renewable energy generator. Software tools can model the details of generator machines and controls and detailed electrical circuit and load models in order to determine if the system will return to stability following a transient event such as sudden change in the output of a specific renewable energy generator. The final section on challenges and solutions will discuss two items related to the effects of energy system integration on a utility's electrical generation systems. 1. Ramp rates and spinning reserves, and 2. Allocating costs and investment. Let's begin by discussing ramp rates and spinning reserves. Sites installing large renewable systems, especially on small utility grids, should realize that a kilowatt delivered does not generally equal a kilowatt saved at the generation plant. It takes time to start a generator and increase its power output, especially a coal or nuclear plant. The heat engine portion of a generator is always operated with some extra reserve capacity to make up variations in the electrical demand. This operational override is called spinning reserve. Without renewable energy generation, the amount of spinning reserve must cover anticipated changes in the load, but with the addition of renewable energy to a system, the amount of spinning reserve must cover both sudden increases in the load and sudden decreases in renewable energy output and at the same time. Spinning reserve is undesirable since it consumes some fuel use and incurs runtime on the generator machine. Much maintenance is planned based on run hours rather than power output. Several strategies have been identified to reduce but not eliminate the amount of waste associated with spinning reserve. Utilities controls may implement sophisticated program logic that analyzes the instantaneous contribution of renewable energy and calculates the appropriate amount of spinning reserve. Storage alternatives to spinning reserve, such as batteries, flywheels, or pumped hydro storage, may be more cost-effective. Demand-side management, or DSM, is another alternative to spinning reserve, which controls the electrical loads on the system rather than aiming to meet all loads at any given time. Forecasting the output of a renewable energy generator minutes, hours, or days in advance also can reduce the need for spinning reserve. Technical developments in forecasting software have allowed operators of utility transmission and distribution systems to predict in advance solar system or wind output. Finally, we discuss allocating costs and resources. Utilities are faced with the challenge of coordinating generation resources and controlling the load demand. Utilities incur costs as they implement the measures described in the previous section and provide the ongoing spinning reserve in order to accommodate distributed renewable energy generation. Utilities argue that renewable energy generation on their system saves them only some portion of the fuel they would otherwise use, and that all debt service, operation and maintenance expenses, and administrative costs remain the same. At the same time, the billing owners that install large renewable energy systems seek to minimize their financial payment to the utility. To equitably accommodate both the residential and commercial customers, utilities are faced with decisions of how to share costs. These discussions may impact the utility's openness to the high penetration of renewable energy. Also, renewable energy is characterized as a high capital cost but a low operating cost. The marginal cost of solar and wind power is essentially zero compared to substantial fuel costs for the fossil alternatives. This has the effect of suppressing wholesale prices paid for fossil energy when renewable energy is generating. This affects the current investment model for utilities and creates a problem for investors expecting a high rate of return on large coal and nuclear plants. To resolve these challenges, a new business model is needed that will reward low-carbon energy production, covers the cost of reliability, equitably assigns costs, and involves investors directly investing in required grid upgrades. Rather than recovering its costs based on how much energy a customer consumes, utilities in the future might charge for services, such as power reliability and power quality, which a customer does use even when generating its own on-site renewable energy. This concludes the segment of the course that discussed challenges and solutions of integrating renewable energy systems at the building, substation, grid, and utility generation level. This concludes the segment of the course on renewable energy distribution challenges and solutions. We now move to the next segment on strategies to integrate renewable energy. To begin this segment, let's discuss some of the key strategies to increase intermittent renewable energy generation to an existing distribution system. The first strategy is to reconfigure utility circuits to allow power to move from a generator to a load, including locations and settings of network protectors, voltage regulation, and overcurrent protection devices. The second strategy is to distribute PV over a larger area. If PV is distributed over a large area rather than installed all in one place, there is less chance that a cloud could affect the output and the generation is smoothed out over a partly cloudy day. Another strategy to increase intermittent renewable energy generation to an existing distribution system is to smooth out daily delivery. For example, a challenge with fixed mounts facing south is that they would all deliver maximum power at noon. However, by using tracking mounts and different PV orientations, it is possible to smooth out daily delivery with less at noon and more in the morning and evening hours. The fourth strategy presented in this slide is to forecast renewable energy plant output. Forecasting would provide a utility system operator with enough advance notice to ramp up a fossil fuel generator rather than maintain a large amount of spinning reserve. Even a few minutes of advance warning could help tremendously. To continue, here are 3 more strategies to optimize intermittent renewable energy generation on an existing utility grid. Controlling the instantaneous demand of non-critical loads is a good practice. It is less wasteful to turn off an appliance for the 15 minutes that it takes to ramp up a generator than it is to keep that generator running as spinning reserve. The 6th strategy is to store energy. Energy storage is the ultimate solution to many integration problems. Battery technology is improving, and costs are falling in response to this future need for a large amount of renewable energy storage. The final strategy discussed is to adjust how utilities recover costs. Cost recovery may evolve from commodity pricing, based entirely on how much energy you consume, towards charging for services that support your generator and your load. This may include standby charges that charge for the ability to serve your load should your generator fail. To integrate renewable energy into an existing distribution system, the economics of such a project must be considered. The cost-effectiveness of a renewable energy project will be important to assess. A project is cost-effective if it is a lower cost than the base case of buying utility power, the project rate of return is greater than the discount rate, and the savings to investment ratio is greater than 1. Levelized cost of energy, dollars per kilowatt hour, is another metric that is often compared to utility rates and among alternative renewable energy technologies. Life cycle cost analysis can help determine which projects are cost-effective and provide an optimal efficiency outcome. That concludes our discussion of strategies to help increase the amount of intermittent renewable energy generation of an existing utility grid. We now move on to the final segment of the course by comparing different types of renewable energy technology to give you a solid foundation to further investigate the best options for your site. When compared to traditional energy generation like coal, natural gas, and nuclear power, renewable technologies have a relative cost advantage. Increasingly, renewable energy technologies can compete with these technologies and prove to be more cost-effective. Look at your site's specific resources and capabilities when considering a technology's cost. These will have a significant impact on your costs. Each technology has different opportunities and constraints. The following table will highlight the resource capacity, various technologies, capital and operating costs, and specific successes of 6 renewable energy technologies. Let's start with solar energy. Solar PV panels convert sunlight to electricity and can be found in panel-mounted or tracking systems. An inverter is used to conduct power conditioning and can be interconnected to a building or utility system. The levelized cost of electricity for solar electric technology, the average price a generator must cover over its lifetime to break even financially, ranges from $140 per megawatt hour to $360 per megawatt hour. The fuel for this system is free solar radiation. Operation and maintenance costs can be around $20 per kilowatt per year as minimum for inspection and cleaning requirements. The lifespan of these systems are around 30 years, with an annual efficiency loss of 0.4%. Solar thermal technology involves the use of a solar collector to convert solar radiation into thermal energy and includes pumps or fans which actively transfer heat to storage or direct distribution to its intended use. Collector types vary by application and temperature requirements, but include on-glazed metal and plastic flat plate collectors, glazed flat plate and vacuum tube collectors, and concentrating collectors. Solar thermal technology contributes 0.1% of Canada's renewable energy mix and includes an estimated 544,000 square meters of operating solar collectors since 2007. Next, we consider wind technologies. Wind energy technology converts kinetic energy from wind to electricity using rotating turbines. Note that the operation of wind turbines in cold climates such as those found in Canada involves additional challenges such as ice accumulation, cold weather equipment failure, and limited or reduced maintenance access. The levelized cost of electricity for wind energy technology ranges from $65 per megawatt hour to $315 per megawatt hour. The fuel for this system is free wind energy. Operation and maintenance costs can be around $50 per kilowatt per year. The lifespan of these systems are around 15 to 20 years. Now, let's compare biomass technologies. Biomass energy is power generated from organic material, for example, wood, agricultural crop residue, aquatic plants, animal waste, etc. Power can be generated by directly burning biomass or turning it into biogas through either pyrolysis or fermentation, and then sending it to a boiler for electricity generation. Biomass can also be co-fired with coal to reduce a coal plant's overall greenhouse gas emissions. Levelized costs for biomass energy range from approximately $60 to $280 per megawatt hour. The fuel requires consistent long-term source and transportation of biomass feedstock and has a relatively higher operation and maintenance cost, with variable costs ranging from $21 to $27 per megawatt hour and fixed costs ranging from $20 to $356 per kilowatt per year. The lifespan of biomass systems are around 30 years. Next, we will discuss hydropower. Hydropower technology converts mechanical energy in running water to electricity using hydroelectric dams. The levelized cost for reservoir hydropower ranges from approximately $70 to $280 per megawatt hour, while that of run-of-river hydropower ranges from approximately $95 to $500 per megawatt hour. The running water is a free resource. Operation and maintenance costs are low compared to other renewable energy generators, and hydropower technologies have a 30-year lifespan. Finally, we will discuss geothermal energy. Geothermal energy technology uses the heat stored in the earth to generate energy in the forms of heat or electricity. Geothermal technologies include heat pumps for heating and cooling buildings and steam turbines to generate electricity. The levelized cost for this technology ranges from approximately $90 to $600 per megawatt hour. The geothermal heat energy source is a free resource, although there are costs to extract the heat from the earth. Operation and maintenance are approximately $70 per kilowatt per year fixed and $3 per megawatt hour variable. Geothermal energy generators have a lifespan of 15 years. This concludes the course material of Integration of Renewable Energy Systems. This course has provided you with the preliminary information and resources you need to consider renewable technologies for your site. Let's summarize what we've learned. We started by introducing the motivations for integrating renewable energy and some of the key sources of renewable energy in Canada. Next, in the Energy Systems Integration section, we learned how increasing amounts of intermittent renewable energy can be controlled to realize cost savings and improve reliability. We discussed the impacts of renewable energy systems on the electrical distribution system, then looked at challenges and solutions for distributing renewable energy at the building, substation, grid, and utility levels. Then we outlined some strategies available to integrate increasing intermittent renewable energy generation on the utility grid. Lastly, we provided an overview of the comparative performances and cost of various renewable energy technologies and outlined their advantages and disadvantages compared to traditional energy generation. With smart planning and resourcefulness, your site can meet energy and sustainability mandates and lead the way in promoting energy efficiency and clean energy solutions. We hope you have learned a lot about this important topic and feel better prepared to move your site's renewable energy plan forward. Thank you for joining us, and we hope that your efforts to implement renewable energy projects are successful. Test your knowledge by completing a short quiz on the course material. Question 1. When determining the viability of renewable energy technologies for your site, consider A. The current cost of energy for your site and local renewable energy resources, B. Installation and maintenance costs, C. Provincial/territorial and local utility policies and incentives, or D. All of the above. The correct answer is D. All of the above. Question 2. According to the 2016-2022 Federal Sustainable Development Strategy and the Greening Government Strategy, the federal government has committed to reducing emissions from their operations by 40% below 2005 levels by 2030 and by blank percent by 2050. A. 50%, B. 90%, C. 80%, or D. 65%. Correct answer is C. 80%. Question 3. Interconnection issues with on-site renewable energy generation projects may include A. Cycling of equipment that regulates voltage, B. Reconfiguration of overcurrent protection scheme, C. Power factor required of the utility, or D. All of the above. The answer is D. All of the above. Question 4. Things to consider when renewable energy contributes a significant portion of an individual building's energy, high penetration, include which of the following options? A. Sizing of electrical service to the building. B. Overcurrent protection on electrical service. C. Network protectors in network grids. Or D. All of the above. The correct answer is D. All of the above. Question 5. Things that the utility company or grid operator would be concerned about related to the integration of on-site renewable energy on utility grids include A. Voltage stability. B. Synchronization of generation equipment. C. Wear and tear on building equipment. Or D. A and B above. The correct answer is D. A and B above. Voltage stability and synchronization of generation equipment. Question 6. Interconnection challenges become greater as a renewable system A. Gets closer to a local voltage regulation device, B. Gets larger, C. Gets farther away from a substation, or D. B and C above. The answer is D. B and C above. Gets larger and gets farther away from a substation. Question 7. Spinning reserve aims to meet all loads at any time. An alternative to this, which controls electrical system loads, is A. Allocating costs and ramp rates, B. Ramp rates and tiered investment, C. Demand-side management, or D. Synchronization of voltage. The correct answer is C. Demand-side management. Question 8. As renewable energy generation in a system increases, A. Conventional sources of power must be increased, B. Central power generation must be equally decreased, C. System operation must be altered to accommodate intermittent renewable power, or D. None of the above. The correct answer is C. System operations must be altered to accommodate intermittent renewable power. Question 9. Strategies for increasing the amounts of intermittent renewable energy generation on the utility grid include A. Controlling the instantaneous demand of non-critical loads, B. Smoothing out daily delivery and generating more power in morning and evening using solar tracking, C. Forecasting output to provide advance notice and avoid large amounts of spinning reserve, or D. All of the above. The correct answer is D. All of the above. Question 10. Most problems with intermittent renewable energy generation on the utility grid could be avoided with A. Improved battery technology and energy storage, B. Synchronizing voltage stability to the electric grid, C. Allocating costs and investments to spinning reserve, or D. Installing network protectors at the grid level. The correct answer is A. Improved battery technology and energy storage. If you have any questions about this course or are interested in other training opportunities, do not hesitate to get in contact with the Office of Energy Efficiency using the contact information provided. Our email address is nrcan.greeninggovernmental-vert.rncan@canada.ca, and our website can be found at www.nrcan.gc.ca/greeninggovernment. Thank you for participating.